Good morning, everyone. I hope everyone's enjoying their Sunday. Happy Memorial Day weekend. This is the YouTubers Hamfest 2021, of course, and I have a very special guest this morning. This morning for me, probably lunch for some others, but we're going to be talking about grounding, shack grounding. I think it's a fantastic topic. So many people just might be doing it wrong. Dare I say that? But let me introduce you to my guest here. His name is Dereck. Dereck, why don't you introduce yourself, your call, and where you're located?
Okay, my name's Dereck Campbell. I am known as KF5LJW, and I live in Tulsa, Oklahoma.
Excellent, excellent. And how the heck do you know so much about grounding?
Well, early in my career, I went into communications in about 1980 for a utility company, electric utility in Oklahoma. And I worked for them up to about 89 until the big telecom boom started. And I jumped ship from a utility and I went to work for a little company called Wiltel out of Tulsa, Oklahoma that grew up to be MCI WorldCom. And during my tenure there, I was the manager. I started out as an engineer in facilities engineering and transport. Did that for a while, and they learned about my background in utility and power. So they put me in charge of what they call infrastructure, and that's basically people that do in the Bell and communication world be the power protection engineers. But we built all the facilities, DC power plants, protective grounding and lightning protection systems, and it also got me into the NEC on the code making panel. And Sarah, and I had to go to several seminars, and especially on the power and grounding side in the telephone companies, I got exposed to the pioneers in lightning protection for radios and data centers and phone offices. And I've actually had some background in writing and authoring some of the IEEE Emerald book, a little bit of a hand in the TIA, grounding standards. So I've worked with all the high performance grounding standards. The people invented it. And basically, I've been doing that for my whole career for the last 30 years.
Well, excellent, awesome. That is quite the story. I can only hope to have such a successful and knowledgeable career. Hey, so we're gonna jump right into it. Dereck here has actually made an autopilot presentation, which is kind of fun. He's going to be narrating through it there. And then what we'll do is please hold your questions towards the end. We've got a whole about 10-15 minutes just for questions there at the end. This is going to go until it's an hour and 15. So 10:15 my time. It's 9 o'clock. So Dereck, let's go ahead and start that PowerPoint.
All righty, so here we go. Okay, welcome to Amateur Radio, Bonding and Grounding Made Simple by yours truly, myself, Dereck Campbell, KF5LJW. Okay, as a point of references, I got a few things you might be interested in. I'm a moderator on Mike Code Forum, and Mike has a real good PDF on amateur radio antenna. And the easiest way to find that is just to do a search term, Mike Gold, Article 810 PDF, or you can always see the link right here if you want to copy it down. To the full link of this particular series, you can find it on Repeater Building. Again, you can just search grounding. And if you want to get a hold of me, you've got my email address here at the bottom, groundguru@yahoo.com. Okay, hopefully today I can make the grounding pretty simple, take some of the mystery out of it. I'm going to define and talk quite a bit about single grounds. We're going to cover some basic AC and DC circuits, particularly AC branch circuits in your home and your DC power supply circuits. Then we're going to talk about equipment ground planes. Then we're going to build a station and cover a little bit on mobile grounding if time permits at the end, okay? Okay, time to bust some myths, and let's start with ground rods. A lot of people fall into this, even technicians and engineers. Earth grounds are 0 volts potential, presumably with respect to each other. That is completely false. There is a gradient, a voltage gradient, that falls across the surface of the Earth. You drive 2 rods in at 2 different points, they're at 2 different potentials. A big driver of this is utilities. And you can actually measure the voltages and currents with the D&M and the oscilloscope. DC, you can also see some DC current and DC potentials out there. Those will
We lost a little audio there, Dereck.
come from airports and
There it is.
pipelines and such other companies that use cathodic protection systems on the grounding systems. Fact is we do use the Earth as a zero reference point. We can bond as many rods as we want together, but we only bond to that Earth electrode one time. It's our single point reference point. And if we do that, that ground will be free of current, voltage, and noise. Okay, myth number 2. Wires have low impedance, therefore conducts electric currents effectively and efficiently. To be efficient, must have low impedance. The facts. It's only true at power frequencies. A length of wire has both DC resistance plus AC impedance. Wires are inductors. DC resistance are entirely dependent on the cross-sectional area and its physical length. Impedance, on the other hand, is almost entirely dependent upon length and frequency. The cross-sectional area has very little to do with the wire's impedance. Okay, single wire circuits like grounds and antennas have high impedance to RF, therefore make poor conductors unless you do something about it to make them be conductive. Myth 3 is a good one, or more of a misunderstanding. You must isolate yourself from AC ground. Well, like I said, a lot of us misunderstand that. It is true you want to isolate your electrical systems, but you cannot isolate yourself from the utility ground. That would be both dangerous and very prone to noise. Example, you can isolate your AC and DC power systems so operating and fault currents in one system do not mix and interfere with each other. Think of it like an RF mixer. You combine two signals in a nonlinear environment to generate a lot of noise and harmonics, right? And then you pick off one of the useful ones with the filter. Bottom line is the NEC does require all systems to be isolated and use a single point ground to do so. And I'm going to show you how to do that. Okay, myth number 4. Every shack needs an RF ground to facilitate efficient antenna operations and mitigation of RFI, EMI issues in the shack. Okay, this is just not possible, guys. Many mistakenly call their station ground an RF ground, but that's not what it is. Later, we'll go in deeper and you'll understand how high impedance makes it impossible to have anything called an RF ground. But station ground is really for your safety. The station ground is used to bond all your radio equipment that doesn't have a 3-wire power cord attached to it. Ever notice a ground terminal on the back of a lot of your radio equipment? And that's what it's there for. NEC requires that hardwire equipment have a hardwire ground. And some may refer to RF radios used on a vertical antenna as an RF ground, but that really has nothing to do with what's going on with the shack. All single wire grounds in the shack are equipment safety grounds, and that's their only purpose. Okay, so why do we ground? Well, it's pretty obvious. We got to make it safe and operational. Fortunately, we can do both, and it's extremely easy when you configure things correctly. How, where, and what order you connect things matter. But I'll tell you right now, both safety and performance can be optimized to the point you cannot improve upon it. All the best practices, like Motorola R56 and ARRL, specify single point grounding. And since 2011 code cycle, NEC 250.94 requires single point grounding. There are 4 primary functions of interest to HAMs. Let's get started and cover them. Number 1, provides a planned fault path to Earth for outside faults like lightning and utility high voltages. Conservation of energy laws state electrical energy always returns to its source. Utilities use Earth as a return circuit conductor back to the generating plant, and the Earth is a return conductor for lightning. NEC 250.50 requires us to provide a ground electrode system. It provides a planned path back to Earth. Think of Earth ground as an absorber or current sink for lightning and high voltage utility faults. So the number one reason is to protect you from the outside world and keeping lightning and high utility voltages from entering the shack. Okay, number two, provides the planned fallback back to the source for all internal power source wiring like AC and DC branch circuits. It enables fast and efficient operations of the breakers and fuses. Let's not confuse this with the number one. This protects the wiring inside the shack and consists of two subsystems: your home's AC wiring system and the shack's DC power system. The green wires in your AC branch circuits and power cords and your DC equipment grounds from your station ground. Protects all the wiring inside the shack. Number three, it's our 0-volt reference for everything. And by everything, I mean coax, cable TV, telco, AC, any services coming to your home. Under normal operations, provides your 0-volt touch potential on equipment chassis, raceways, enclosures, and equipment frames. If you were to have a line to ground fault, it's going to limit the touch voltage on the equipment chassis and prevent electrocution until either the fuse or the breaker operates to clear out the fault. But the hand is kind of the holy grail because it is your 0-volt signal reference. Okay, but NEC and best grounding practices do not permit normal operating currents to flow on grounds. Only fault currents are permitted. If you allow current to flow on your ground conductors, it's going to develop voltage on those ground conductors. And it's just simple as Ohm's law. So any unwanted voltage and currents are noise. Number four, Pico Lightning, also known as static. It's pretty self-explanatory, so we won't go into it much here, other than that's the fourth reason and the last reason we ground. So if we can cover those four bases, we're off to a really good start. Hands have two unique challenges facing us, and it's hiding in plain sight. The first challenge is we use radios with a 12-volt, 2-wire power and grounding topology. It's not compatible with 3-wire power and grounding topology we use in our homes and offices and businesses. It forces normal operating currents onto the ground system, and it corrupts it. The second challenge is we unknowingly place our equipment in a ground loop. We talked about ground rods early in myth number one and placing ourselves between two earth grounds. Well, as you can see on the picture on the right, that's typically what we do when we bring the AC service and our coax into two different places. We place ourselves between the two earth grounds. And ground loops can be extremely dangerous. It provides a direct path for volt currents to enter our house from the outside world and a place to exit. Okay, so we got to get rid of that. And additionally, under normal conditions, it'll force RF currents and just common mode currents flowing through the house because these two earth grounds are always at different potentials. So there's always going to be equalizing current. Key up the transmitter, now you got the RF current on it. Okay, let's talk about 3-wire versus 2-wire topologies. There are two distinct differences between 2-wire and 3-wire power and ground topologies. The two methods operate differently and are not compatible with each other. In a 3-wire system, the grounded circuit conductor neutral is only bonded to ground once per code requirements. Example, your AC service neutral is bonded to earth at the service entrance meter can. Equipment ground conductor and neutral are electrically isolated from that point on. EGC is an open circuit with no normal operating currents flowing or voltage present. Essentially, it's a green wire stuck in the mud, creating our 0-volt reference point. Now, if you look over here on the right, we can see that. We can see the line conductor. It goes to the load device. Okay, the load device is represented by our resistor here, and all the current returns on the neutral. Back here at our service, or wherever the source of the power is at, the neutral is bonded to ground, and then they're kept electrically isolated. This chassis is in the ground are completely an open circuit. There's no normal operating current. Now we drop down here and contrast that to a two-wire system. The grounded circuit conductor and ground are essentially the same conductor. Inside every 12-volt device, the grounded circuit conductor, negative, is bonded to the equipment chassis. Result is you're going to have current and voltages on all conductors, chassis, and raceways. Best practices in electrical codes do not permit current to flow on grounds. It can leave you with noise defects, and you're forcing normal operating currents on the grounds. Now, just contrast it and go over here and look and see what's happening here and why that can become important. So, all the current being supplied by the battery is also using the ground as the same conductor back to the source. So what's happening here is your zero reference point is constantly changing. Why is that? Because if we remember, we know we have an impedance between these 2 points. Okay, we've got current flowing through it, so that means our voltage we're incurring a voltage drop. Think about your car, even on the DC side. The DC voltages you can lose. Same thing's going to happen with signals. So our signal reference point is constantly changing. Now, if our ground didn't have any current flowing, it's never changing. Okay, let's talk a little bit about your home AC branch circuits under normal operation and kind of see how the whole thing works. A lot of misconceptions about what some of it does and does not do. So let's get oriented here. On the left, I'm showing a utility transformer with a 2-watt service to your main breaker panel. You can see the 200 amp main breaker here. Then you can see your distribution breakers. And I'm showing a 20 amp breaker for this particular circuit. From in your meter panel, the neutral or the center tap from the transformer is the neutral conductor. And it'll come into either your meter can or your meter panel, depending on how it's laid out. You're going to have the ground electrode system with a ground electrode conductor coming up, and it's going to be solidly bonded to that neutral. And it'll also be solidly bonded to the service can or your meter panel, or your breaker panel, excuse me. Then from your breaker panel, we go out to distribution. For distribution, we'll start with the ground wire, and that's the green wire that goes with your AC branch circuit. It'll go right to the wall socket. You'll also have the white neutral conductor going to the socket, and then up here at the top, you'll be the line conductor, which is called hot, and it's on a 20 amp breaker. And what I'm showing out here on the end is a device plugged in. We can see the power cord with its 3 representative conductors. Take note that this is a 3-wire system, so the ground and neutral has no bond. The ground circuit has no electrical connection with the AC circuit at all. It's completely isolated. Okay, so we turn the power on. This device, it can be anything, but it's drawing about 600 watts. And at 600 watts, it should draw about 5 amps of current with 120 volts applied. And if you look, I've got these little red arrows, and it's showing us the current path, normal operation. And you can think of this as a battery or anything you want right here. We've got the current leaving on the line conductor, going to the fuses, the distribution, out on the line, through the device, and then it returns right back on the neutral conductor, goes right back to the transformer. All right, everyone see that? Now, some think that ground and neutral are the same thing. This is not true. The neutral or grounded circuit conductor, it carries normal line current, normal operating line current. The ground does not. It does not carry any current whatsoever. It has 0 current. Another thing you can do to look at your power quality, if you were to look here at the wall socket or at the device, we should be able to measure voltage between ground and neutral. You should see a little bit. If we're drawing a lot of power, say this was a toaster oven drawing 1,500 watts, we may see as much as 2 to 3 volts. And if we see 2 to 3 volts here, we know we've got just about that much sag on the line. So our total line loss would be 4 to 6 volts. Everyone see and understand that? Because we're taking loss on this conductor and we're taking loss on the neutral. So there's going to be a voltage loss along the lengths. So we're looking at a voltage sag, and that's one measure of power quality. And if you want to know what the number is, 2.5 volts is the maximum limit, and that would be at 15 amps. So what is ground doing? Well, it's pretty obvious. It's holding this chassis at 0-volt level. It's also, if this were to use the ground as some sort of signal reference, it would also be our 0-volt reference. So that's pretty much how your home circuits work. It's really pretty simple. So let's take a look at the next slide and see what happens when a fault comes along. Okay, now let's take a look at a fault condition. For whatever reason, the line conductor inside the chassis has fallen off and touching the chassis, line cord got pinched, whatever may have happened. So now we have 120 volts in contact with the chassis, and now the ground completes the circuit. And if we follow the current, we can see the current path is off the equipment ground. It goes straight back here to our neutral bus inside our main breaker panel and return to the utility. Now then, since there is no more load device from line to neutral, it's line to ground, it's a short circuit. And being a short circuit, it's going to draw, should be 120 to 300 amps. Now, the reason I know this for working with the NEC for 6 years and working with the codes for 30 in practice, it takes 120 amps to be able to induce enough fault current to trip a 20 amp breaker within a half a cycle. So in other words, for a breaker rating, you want to have at least enough fault current to be 6 times the rated current. In this case, 20 amps times 6, 120 amps. And it could be as high as 300 amps if this 14 gauge, 12 gauge, if you're going by code, were to be a very short circuit, very close to the panel versus, say, a long circuit out to the other end of the house, and then you may only have 120 amps. Now, notice what ground is actually physically doing at this time. Notice that Earth is really, it's doing something, but it's not in the fault path. Everyone see that? Earth is not in the fault path, and it's done intentionally that way. You cannot use Earth as a conductor. Let's say if we could make a 10 ohm ground, instead of having this wire, we just have it go to Earth, and we got 10 ohms. Well, think about 120 volts with a 10 ohms circuit is 12 amps of current. Well, what's 12 amps going to do to a 20 amp breaker? Nothing, right? So as you can see, but ground is doing something. Think about what's going on here. We've got 120 volts applied between right here on the line and right here also on the ground and neutral. Each one of these conductors is the same size, 14 gauge, and they're the same length. Right here at this chassis, we've got a perfect voltage divider. So what it's doing under that fault condition for half a cycle, there'll be about 60 volts on this chassis. So it's limiting the potential to tolerable limits so you don't get electrocuted. And it should operate within, induce at least 120 amps, which would be about a half a cycle, 120th of a second. Okay, let's expand the circuit a little bit. We basically have the same circuit we just seen with something added on. Over here on the left is coming from the utility is your AC breaker box. This would represent the line coming from your 20 amp breaker to your wall socket for your DC power supplies, which sits right here. And the DC power supply is now feeding your radio, that mysterious black box that we had out there. And this is in the shack on the opposite side of the house. And from your radio, we go out with our coax to the tower. We have our coax shield bonded to the ground rod. And if we follow the code, we knew we had to bond this ground rod to the AC service ground rod. So let's take a look at what happens here when we apply the DC power. As we leave the positive, it comes through our radio. We reach the negative, and it splits, and current goes in 2 directions. The one is the intended and planned path, the black wire that we ran back to our power supply. But the second direction is out the coax, back to the bonding jumper, through the dirt. It comes back up out of the ground, and it heads back right to our AC panel box, and then onto our AC equipment ground that we ran out to our wall socket, back onto the chassis of the DC power supply, finally back to negative. That causes us a couple of issues. One, if you've ever wondered what the 60 hertz hum in your transmit and receive audio is, this is a good source of it. The other thing it does, by running DC current with a negative polarity, it causes corrosion to all our ground electrode system buried down here in the dirt. You've got moisture and acidic conditions, and it just sets up the perfect conditions for corrosion. Now, in the industrial and commercial side of it, radios, we do bond the battery, but we bond the positive, because if you bond the positive, you don't have corrosion on the system. You actually have galvanic protection. So I think you can clearly see the problem, and the result is you bonded the grounded circuit conductor twice. That forces ground to be in parallel with it. Okay, now it gets ugly. We're going to do some fault. For whatever reason, working on the power supply, doing whatever, we've pinched the line conductor. It's fallen into the case. And now we want to take a look at the AC fault current. So let's take a quick look. One, in the chassis, it returns back onto the AC equipment ground, the one that's planned and intended for it, goes straight back to the utility. But with that bond in the power supply to the negative, there's a second path. It gets on our DC negative, it goes to our radio. It goes through our radio equipment out on the coax, back to out here onto the earth ground, comes all the way back through the earth ground to get back to the utility transformer. Okay? That's not good. There's no reason to have that, and all we got to do is isolate the two systems. So this is where you hear you want to be isolated from the AC systems is exactly correct, but they must have a common path. So how do we do it? Okay, again, the same circuit, except now we've made a modification. We can't get inside your radio and get this bonding jumper out, okay? That's just impossible. But we can fix your DC power supply. There's absolutely no reason for that bonding jumper to be in there. Okay, there's no code or equipment requirements that require that jumper to be in there. It doesn't serve any purpose. It's a troublemaker. So we can get in there and take it out. And now then, we have AC and DC isolation. Under normal operations, note what's happening. Current leaves the DC power supply, comes through our radio, and every bit of it returns straight to the power supply, back on the DC negative conductor. Exactly what you think and the way you think it should work and how it should work. Okay? Pretty simple. What about a fault? Okay, wrapping up AC-DC isolation here, I've induced two faults to see how it all works. So on the left, we've got an AC fault line to ground or line to chassis. It returns straight back to the utilities neutral through the equipment grounding conductor that ran with the house wiring circuit. The DC side, if we have a DC fault, it's contained right here. It's returned right back to the DC power plant, the source of the power. Now, the one fault I didn't show would be a primary to secondary transformer fault if 120 volts appeared over here on our DC side. Well, that's why we have to have a common ground point, and that's exactly what this does. A 120 volt fault would be returned to the utility right along through this bonding jumper that we have down here in the ground, back up to the AC panel box, and returned right back to the utility neutral. That's how we keep it isolated. Okay, let's talk about differential mode currents and differential mode circuits for a moment. Differential mode circuits are circuits where voltage or signal is applied between two circuit conductors. Some examples have to be your coax interconductor to shield, or plus to minus on a DC power circuit. Current flows out on one conductor, it returns on the other. Current in each conductor is equal and opposite in polarity, and the sum of the two currents are always zero. Differential currents do not radiate. They've closely coupled together with this opposing circuit conductor. Example like a transmission line. Differential mode currents are the currents hams and all of us are familiar with using everyday circuits. And here are just a few examples of differential circuits. And I'm not going to spend a whole lot of time here with them, but you can kind of see and get the idea. The current leaves out from the power source, and all of it returns back to the power source. It's contained on the two circuit conductors that we normally use and think of. Okay, so that's really about all I'm going to cover on that, but keep it in mind because it becomes important. Common mode circuits are the troublemakers, and ironically, it's what makes our antennas work. Currents are flowing on a circuit conductor without an equal and opposite circuit conductor like we use in a differential circuit. It's current flowing in the same direction on the one or more conductors. Its common mode currents make multi-conductor circuits behave like a single wire circuit or an antenna. The source is common mode circuits are also the source of all your shack-generated RFI and EMI issues. Common mode currents both radiate and receive signals, and they're hiding in plain sight, and frankly, we don't see them and recognize them all the time. Okay, let's go back to where we were a few pages ago, back to our DC power supply, before we pulled the jumper out of this DC power supply, and also compounded by the jumper in our radio equipment. We are forcing common mode current in this application. It's DC. It doesn't necessarily cause us any real noise problems, but it does cause us some corrosion problems. But the main reason is because we've bonded a neutral conductor, our reference conductor, that we bonded to ground. We've done it more than one place. We've done it twice. So we're forcing some of the current we're taking current off of the return, our planned return path, the black wire from the radio back to the power supply, the one we know about. But with these jumpers in there, it's also forcing some common mode current to flow. So this is just an example of how it can happen. There are other methods and mechanisms that cause us the real headaches, and we're going to take a look at some of those. Okay, in our next example here, we have a classic performance grounding textbook example of how they demonstrate common mode noises. Showing everything kind of compounded together and how it all adds up. Over here on the left, you see we've got the utility, and they're basically showing you how the utility is able to inject current into their ground system, into the earth, because at every pole they have what's called a multi-grounded neutral. At every pole, they've got a ground conductor, the pole ground, coming up to the top, and it's bonded to the neutral. That's in parallel. That puts earth in parallel. And as they state here, most of the current on the neutral is actually flowing through earth. Well, as that current flows through the earth, there's a voltage gradient developed along the ground. If you remember earlier, I said that ground rods are not at 0 volts with respect to each other. Each ground rod is at a different potential. So those of you who might be working in the industry, telephone offices, you might recognize this drawing, or at least the circuit. It's showing how the outside influences are pushing a current through this whole system. Here we've got two different buildings, data and telemetry cable going between them, and their earth potentials are at different voltage potentials. So basically you've got a battery between these two pushing common mode currents. Okay, the next example should bring it home. Okay, a key takeaway point, and something we've been talking about for the past few minutes, single wire circuits that we use are for equipment grounds and antennas only. A single wire circuit does not have an associated circuit conductor ran with it to cancel out the mutual inductance. As a consequence, single wire circuits operate in common mode and encountering very high circuit impedances proportional to the length and frequency of the conductor. Okay, it's simple Ohm's law. No reason to get lost in the math. We all know that 6.28 times the frequency times the inductance equals the impedance. The longer the wire, the more the inductance there is in the wire. Okay? Let's see, single wire circuits are only efficient conductors at power frequencies of DC to 60 hertz, where resistances and impedance measure in micro and milliohms. At RF, impedances varies between 30 ohms up to several kiloohms at half wavelengths. Single wire circuits both radiate and receive signals composed of both RFI and EMI signals. At the lower frequencies like AC power and AF can generate and receive EMI, and at RF can generate and receive RFI. So how do we make wire conductors low impedance with no resistance so we don't burn up and waste all our power as heat on our wires? Well, it's actually pretty simple, as you'll see. Well, the answer is pretty simple. We use a transmission line. All the transmission line is two or more conductors coupled closely together so that they cancel out the mutual inductance between the conductors. Transmission line operates in differential mode where the currents are equal and opposite in each of the conductors. Now, as hands, we're aware of a few types of transmission lines we use, like coax and ladder line and such, but there may be some other forms out there that we don't recognize them when we see them. Example, all your AC home power circuits are required by code to use a transmission line. And you can see an example over here, this yellow cable. It's called NMB, that practically every residential home is wired up with. Now, the primary reason for doing that is for AC faults, line to ground faults. We don't want that impedance interfering with the breaker operation. If we allowed that extra impedance to be in there from the AC impedance, it could impede fast and efficient operation of our circuit breakers. So what do? We make a transmission line out of it. DC power cables, same thing. And it's especially true today with our digital nature, and especially some of the digital modes where the current is off on, off on. That gives it an AC signature. And if we had a lot of inductance in the line, we're going to get some ringing and noises. Audio lines, speaker lines, telephone, data, Ethernet, you name it, they all use transmission lines to get rid of that inductance and leave us with purely low resistance, so we don't lose any power when we transmit power or signals from one point to the other. Okay, time to talk about equipment ground planes. You've heard me reference to it a few times and might be wondering what I've been talking about. It's really pretty simple. It's a little conceptual, but it's very real. So let's get into them. Every electrical system or electronic system has an EGP, or equipment ground plane. Its performance and its size can be measured with predictable results. The EGP is a common mode path between the system's input and the system's output and everything in between it. To understand what it is, it helps to draw it out to see it for the first time. It is a one-line diagram showing how all the components are interconnected that make up the full system. It would be the path either DC current or AC current would take from the input to output. So let's have a look, and you should get a pretty good idea here with the next slide. Okay, let's take a look at a typical ham radio operator's equipment ground plane. To get you started and oriented, let's go over here to the left side, representing your AC service, whatever side of the house that may be on. And the opposite end over here is going out the ham shack at the other side of the house, and everything in between it. So we start out at this ground rod. This is where our ground plane starts. It goes up to the AC breaker box, gets out on the branch circuit, goes out on the 14 gauge wire to your wall outlet, to the power cord, and that distance may be, 20, 100 feet to our DC power supply. In our DC power supply, we got that pesky jumper that we left in there, and it now puts the ground plane onto the DC negative going out of the power supply, which is not a ground at all. We get onto the chassis. From the chassis of our radio, we're out on the coax shield to a linear ramp, out on its coax shield and on down the line until we go back outside, back down to the ground rod. That distance measured, it could be 30, 100 feet. Also notice we don't have a ground. We have a series daisy chain. that is not a ground. Right below, we can see the problem where the circuit's been simplified by these resistors with an AC source driving it. So this resistor here represents the AC breaker panel resistance. This resistance here equals that wire's impedance. This would equal the DC power supply impedance, on so down the line until we complete the circuit. So we know we got a difference of voltage between these 2 points. We know we have to have common mode current flowing through here. Ohm's law tells us if we have current flowing through a resistance, we have a voltage drop across each of the segments. It means everything's at a different voltage. Okay, we can measure the performance of your equipment ground plane. To do it, we have to measure at the 2 furthest points of the plane. So a typical plane, that's going to start at your AC service ground, and the other end of it's going to be several feet away at outside the shack window at your ADU. That could be, I don't know, as short as 20, 30 feet, maybe as long as 100 feet, if not a little longer. Point is it should be measured in inches, not tens of feet. Same with electrical performance. The same, we measure at the same 2 furthest points. We put our probes on the AC service ground and the other end on the ADU ground. You can turn all the power off and measure the DC resistance. With that long circuit, you're going to be measuring half ohm to 1 ohm. You should be seeing 0 ohms. Same with AC impedance, if you were to measure it. You could do it with a VNA, and ideally, again, it should be 0 ohms. But it's not. I can tell you, it's going to be up around as low as 30 ohms at quarter wave and odd quarter wave resonant frequencies, up to several thousand ohms at half wave intervals. So essentially, your equipment ground plane is an antenna. Continue with the test, measure the AC voltage with everything off, then in receive and transmit modes with the transmitter at maximum transmit power. Ideally, all 3 should be 0 volts again. You're going to see several volts in the transmit mode and maybe a few volts in receive mode, and even with everything turned off. Measure the DC voltage same as you did the AC voltage. Ideally, all 3 tests should be 0 volts again. If you do not pull that jumper out of the DC power supply that we've talked about, you're going to see some DC voltage during transmit. Last, use an oscilloscope and observe the signal's magnitudes and frequencies. Measure it all with everything off. Again, in receive and transmit modes at maximum transmitter power. And again, you should see a flat line. Good luck with that, okay? It's not going to happen. The takeaway is you want your equipment ground plane to be as small as possible with as low of an impedance as physically possible. It just makes sense. It's a single wire circuit. Otherwise, equipment's going to all be at different voltage potentials, and you're going to lose your 0 volt reference point.
It's showtime.
Okay, time for the magic of the equipotential ground plane. We're going to repeat the test, but we're going to modify the ground system a little bit. We're going to bond the input and output together solidly. We're not going to do it with a wire. That would defeat the purpose. Physically bring the input and output to the same point. We bond them together on a bus bar side by side, less than 1 inch apart on solid copper or an aluminum bus bar. We don't have to do the test to know what happens. All the measurements go to 0, except for the size. And we've reduced the size to the greatest extent possible, down from tens of feet down to just a few inches. What we've done is we've moved the equipment ground plane off the actual radio equipment and all the wiring and relocated it onto a ground bus where we can manage it. We can shrink a big office, say 40,000 square feet electrically, down to just a square foot of a bus bar. Unlike a single wire ground system with unacceptable impedance between points, an equipotential ground plane has no resistance or impedance between the 2 furthest points on the plane or the opposite corners of a bus bar. So if we don't have any impedance, it means we can't have any voltage differences across that plane. And if we don't have any voltage differences, it means there's no common mode current flowing through any of our equipment. We got a squeaky clean ground system free of voltage and current. Everything's at the 0 volt, or excuse me, everything is at the same 0 volt reference point. That's the magic of the single point grounding, and it's really no magic at all. It's just basic fundamentals. Realistically, there are limits to how large a ground plane can be because there is some resistance and inductance involved. If we limit the size, height to weight ratio, and the arrangements of the conductors as they fall in the ground bar, we can keep the impedance to low tolerable limits. Now, in the studies from Bell Labs, National Lightning Institute, and some other listing agencies determined a 3-foot radius is the maximum size you can make a ground window. And all that means is if I were to install a big old 8-foot-inch tall by 6-foot long ground bar of a 1/2 inch in thickness with the earth referenced in the middle, terminating to the center conductor, is as large as it could be for 3 foot either side of to the furthest ends of the ground bar. Any larger lightning and utility-induced fault currents could develop enough voltage potential across the whole plane to do damage. Okay, as hands, we're never going to need anything near that large. We'll be working with something more like 4 by 12 or even smaller. So the ground window is where all the cables must pass through before entering or leaving a protected area. And let's not forget about those cable TV and telephone cables. Okay, so let's move on a little bit more. Earlier, I stated where and how you connect ground conductors matters, and this is critical once we get to the ground bar. We segregate the conductors into 3 zones called producers, absorbers, and non-producers, also known as a pan bar. This was done in the telecom and the wireless industry to make it simple for installers so they know where to terminate cables to. So producers are anything like your utility, your telephone company, cable TV, and all your radio coaxes. These are the items that will carry lightning and utility fault in. So it's anything for the outside world you want to protect yourself from. The absorbers, that's real simple. That's your current sink. That's where you want to send all the bad stuff, all the outside world. That's your ground electrode system that's comprised of your underground water pipes, ground rods, radios, and everything you got buried in the ground. So this is where we want to sink and direct our outside faults back to the source. The non-producers, that's all the wiring inside the shack in your house. Okay, let's take a little deeper look at the pan ground window bar and how it works. As I noted earlier, we use a ground bar to manage our ground plane, and that's exactly what we're doing here. In order for current to flow, it has to have an entry point and it has to have an exit point. Now, the thing with outside surges or outside producers, lightning, the utility, they're not looking for our radio equipment. They're looking for earth right down here. So what we're able to do with the pan bar is we're able to bring the producers into one zone and direct it straight to earth. Now out here on the end, our equipment looks like an open circuit to lightning. Okay, there's just no other place for it. There's no place for lightning to go. It only has one path to come into the producer and then leave out into going to our current sinks, our ground electrode system, our absorbers. Okay, traditionally, hands and AC circuits haven't played well together. Neither has a cable or satellite or telephone interface up until the mid-'80s when they finally got their act together. But us hands have kind of lagged behind. Today, NEC electrical codes resolve most of the issues with 250.94, which requires single-point grounding via the intersystem bonding termination. Earlier in the doc, when we started today, I gave you some references. One was a Mike Holt's code form, and he's got several white papers, one on Article 810, which is strictly dedicated to amateur and CB radio operators. And they're showing basically the single point how it's done. Here's a real simple system. We got our tower. We've got our service entrance. You can see our ground electrode system here. And you can see our coax coming in up to right here where it's surge protector. a ground wire going to the GEC, back to the ground electrode system, and the coax going inside. Picture on the right, just a little more detail with 3 antennas, but it's all showing basically the same thing. The only thing we're modifying is we're taking it one step further. We're not using wires to make these intersystem connections. We're going to place a bus bar right out here underneath our meter, or wherever this GEC conductor is, going down into the dirt from our electrical service. You can see it here in this picture. You can see it again here. This is where we'd want to place our ground bar to mount everything instead of using wires. Okay, let's talk a little more about AC circuits. As you know, they're troublemakers. They're going to put you in a ground loop every time if you don't bring your coax in with your AC service. Branch circuits are prone to noise due to the way they're installed. They're daisy chained through your house. Coming out of your main breaker panel, your general purpose circuits going through your house, you may see 3, 4, maybe even 5 outlets, and maybe even some lighting. Now, where this gets to be a real problem, especially for us hands, is what's either plugged downstream or upstream from us, especially like, say, in the kids' bedroom, they got a laptop or their video games. Another room, say the living room, you got a USB hub charger. All these things have line noise filters in them. And this guy right here, these 2 capacitors are real troublemakers. If you look, you've got a capacitor, a 0.1 microfarad capacitor hanging from line directly to ground. Well, that's injecting 60 hertz current directly into your ground circuit, okay? And all that is doing is going back on the ground wire, back to your breaker panel over here, and returning back to the utility neutral. It's current being put on your ground for nothing. It's just a noisemaker, okay? We cannot remove these line filters, but what we can do, we can get rid of the daisy chaining, and all we got to do to get rid of most of these problems is put in a dedicated AC circuit. Okay, let's talk about a dedicated AC circuit. It's critical in a proper power and grounding system in a shack, okay? It ensures you're going to have a clean AC equipment ground with excellent power quality, free of excessive voltage sag, and our harmonic currents being carried on any of the conductors. Now, if you brought your coax directly to the shack, we need to relocate the AC ground from your service panel over to the shack ground and put it onto your station ground bar. And there's a couple ways you can do that. The best practice is to run a dedicated branch circuit on the outside of the house to where the coax enters the shack. That places the loop outside in a protective raceway, so if you do have any lightning events, you've at least got that fault current running on the outside of your house in a protective raceway, and it's pretty easy to replace. Otherwise, it's going to be in your walls and attics and crawl spaces, and you really don't want it there if you don't have to. The other method, of course, is run the dedicated circuit conventionally to where the coax enters. This method leaves a loop inside your home and exposes your walls and attics to those risks if you're willing to do it. But it also can be a little bit difficult to do running a dedicated circuit on an outside wall, which you'll likely have to get it to where the coax enters. And if you brought your coax in with the AC service, you're going to have a real single point ground. The guys who brought your coax in at a different location, you have to create kind of a false or a faux single point ground. But if you bring your coax in with the AC service, you're making a true single point ground, and there's really no special requirements. You run your dedicated circuit in conventionally to the shack wherever you want to put it, and just carry a 6-gauge in with your coax from the AC service for your station ground bar. And I'll detail that a little bit here shortly. Well, there is a third option for our couch potato friends out there, and it's at least better than nothing. The mock-up you see below is the station ground bar with the AC outlet and the surge protector on it, or the coax surge protector. Instead of bringing your dedicated AC circuit right into the back of that bus bar with your coax, you make yourself an umbilical cord using SO 12-3 cord and a NEMA 515 plug. You just rig that up and then just plug it into whatever wall outlet you got, it's going to at least take your radio out of the ground loop. And if there is a lightning event, at least it won't be going through your radio equipment. You'll still have the loop in your house, and you'll still have you won't have a dedicated circuit. You'll still be sharing with something in the house, but you can find those and possibly just unplug everything off of them. So at least it's dedicated only to your use. Okay, here's some minor details you want to kind of watch out for when you're putting everything together. First thing you do, you want to keep your coax as close to the ground level as you possibly can. Okay, the other thing is you cannot run your electrical in with your AC. So when you bring your AC and coax in the house, they got to come in their own wasteways, or in the terminology I use here, a separate porthole. Okay, it's highly recommended. And this is something that not many hams do and they overlook. But you need to ground your coax shield as many times as you possibly can before bringing it in the house. Every opportunity you get, you want to bond that shield. That's bleeding off any static charges or any lightning charges as many times as possible before we bring it in. Okay, and for your convenience, you can use a second ground bar for your equipment grounds at tabletop level. In other words, you can put a ground bar outside with the surge protectors if you want, and then just run your coax in along with your 6 gauge, and that 6 gauge will come up to another ground bar that you can just use strictly for your station ground to ground your equipment to. Okay? Okay, let's talk a little bit about the ground electrode system because it is crucial and it's critical. Now, here's something you need to know and understand. Ground rods are for power and radials are for lightning and RF. Okay? When lightning strikes, it spreads out along the surface, creating what they call a step potential difference. Okay? Where that name comes from is the distance between your feet is enough to kill you. Lightning strikes and enters into the ground. The distance between your feet can develop enough voltage to kill. Okay, radials intercept and direct lightning discharge currents to where we want them to go. You use radials to direct them away from the protected area, like your shack or the tower. Radials should be continuous with absolutely no splices unless thermally welded. A bad ground rod connection does not affect lightning and RF performance. A poor radial connection seriously degrades RF and lightning performance. So the takeaway here is you don't need very many rods. In fact, you don't need many at all. It's radials which are the most important, and the more the better, but do not ever splice them. Try to use mechanical clamps like split nuts, split bolts. Preferred methods, and I know not every y'all can do this, is in the professional industry, pretty much anything outside and underground, it's all exothermic welded or brazed, and we use a lot of irreversible compression, which you can do. But buried mechanical methods, like say a radial or bonding jumper to a ground rod, you can count on it. That ground rod connection is going to fail, so keep the radials intact. Okay, here's just a couple examples of how to run your rods and radios. Of course, we have our house here, as denoted. And if you got the mast on top of your house or a mast near the AC service near the side of the house, this here is a pretty good, simple arrangement. You've got our 3 radials going out away from the house, taking discharge currents away from the protected area of the house. Same thing here on the drawing on the right, except now we got the tower moved out away from the house. It can be up here, back here. It doesn't matter. You need to take everything back over to the AC entrance. But this time, instead of taking several radios away from the house, we just take the one radial out to the tower, and then we can take our radios out away from the tower. Now, there's something else that I want to talk about. There's a difference between RF radials and lightning radials, or your ground electrode system radials, but they can be combined. So out here at the tower, your RF radios can make a really excellent lightning protection system. Okay, the trick is don't use insulated wires. Use bare wires and don't bury them deep, just an inch or 2 below the surface, as deep as you'd want to take your RF radios. Whereas the ground electrode bonding jumpers or radials, you can take them quite a bit deeper, but if you're going to run RF radios, you want them right near the surface so the RF doesn't have to penetrate dirt. like this dirt can't conduct electricity or earth very well. Okay, takeaways. When you reference to earth ground twice, you will place you in a ground loop every time. Best practice is to bring your coax inside with your AC service. Otherwise, countermeasures are required. Inspect your DC power supply for a bonding jumper between the chassis and DC negative. If you find it, remove it. Equipment ground planes, as we learned, should have a low impedance and be as small as possible. Dedicated AC circuits are preferred and must be used to resolve multi-point ground issues. Use a ground bar or such device to manage your equipment ground plane. And to sum it all up, you bond everything below ground together, you bond everything above ground together, then you bond the two together at a single point. And I think we're going to close with that.
That's all, folks.
Oh, man, Dereck, so good. Thank you, thank you. So let's see, I think you wanted to cover some vehicle installation, correct?
Yeah, if we want to cover that now or wait for questions and answers, how you want to do it?
Well, let's just touch on vehicles real quick. A lot of questions. I think you shattered everyone's brain about the little jumper bonder inside of your power supply. So let's just quick. And you know what? We can always have you back on as like a pure Q&A, but let's get to that vehicle information because the vehicle stuff, I bet a lot of people are doing it wrong. So go ahead.
Yeah, actually, you got some of the same common problems that you do inside your house. Okay, mobile installations give us a couple of challenges. Most notably is the incorrect installation instruction and guidelines from our manufacturers, specifically instructing you to connect the radio negative directly to the battery terminal with a fuse inserted. You'll see in just a second why that's pretty dangerous. Automotive electrical systems are a two-wire grounded system, but it is a two-wire system. And where both fault currents, signal reference, and everything is all used on one conductor. The vehicle chassis and frames are used as both the battery return and the ground. Okay, you've got a lot of vehicle currents flowing through the frame and the chassis of the vehicle. If we look at the circuits, you'll get a pretty good idea, but it starts right here. How many of y'all have seen this come from your equipment from your radio manufacturers to specifically wire your radio up like this? Well, take that piece of paper and throw it away, because if you look at the full circuit, you're going to see something kind of ugly. You're going to see a real nasty ground loop. Take a look at what we've got here. This is basically the same circuit that they're showing you here, but now we're adding the vehicle circuitry to it and how it actually works. So if we look at the first drawing over here on the left, here's our radio. We can see the red power lead coming through the radio, and we know that our chassis is also connected to the negative. So here's our negative lead going back to the battery with the fuse, and it's directly across the battery term post. Well, if you go and pop the hood of your car, if you look at your battery negative terminal, you'll see a real heavy negative cable going from the battery negative term post to a hard point on your vehicle chassis. Now, that can be the fender well. You'll see some vehicles on the firewall, but it'll be a heavy cable going right to the vehicle chassis and frame. So look what's going on with our radio here. We've also got another ground connection that some of us overlook. It's called our coax shield, and it's going right from the radio to the vehicle chassis to wherever that antenna is mounted up. So look what we've done here. We've put our radio negative circuit in parallel with our vehicle bonding jumper. All our vehicle current is supposed to return on this particular jumper. Well, now that we've gotten a second pass right through our radio, and you can prove this. You can go out to your car, turn your radio off, and if you've got a clamp on amp meter, clamp it on either your radio negative or your coax and monitor DC current. Turn all your headlights on, everything on, get it going. Even with your radio off, you're going to see current flowing through your radio. That is noise, guys. Plain and simple. All right, that's your zero reference point, and now then you're adding the vehicle current on top of your radio current. Well, if y'all ever worked with a mixer in your radios, how they work, you inject two signals into a linear system. Well, that's exactly what you're doing right here. Your vehicle currents are very much digital in nature, AC, with the on-off switching action. So you're getting a lot of unnecessary vehicle noise added to your radio. Well, what happens if you take your car to the mechanic or you work on it and they have to take this vehicle bonding jumper out, or say you're driving down the road, down a country road, you hit a stick or just wear and tear and you lose that vehicle bonding jumper? You're not going to know anything's happened because now then your radio's doing that job for you. You're not going to know it's a problem until you turn that vehicle off and you go to start it. Look what happens. That jumper's gone. Your starter current is now trying to use your radio up to a couple hundred amps. Okay? Everyone see that and understand what happens? This is not make-believe. This is what happens when you go directly to the battery. It's just simple Ohm's law circuitry. So how do you fix it? Well, duh. You don't go to the battery, you go to the chassis of the vehicle like everything else in your car is wired. So now then, the only current going through your radio is your radio current. You no longer have any vehicle currents flowing through it. What happens if the vehicle bonding jumper comes up missing? Everything's dead, like everything in your vehicle. There's no path. Okay, it's like an open switch. So, with that said, let's just look at some best practice for mobile installations. Run the radio positive directly to the battery term post, as the manufacturer shows. Use an inline fuse. Now, I don't like what the manufacturer supplies. I like to use marine components, and this little unit over here is a marine battery fuse assembly. This part is solid copper with a hole, and that goes to your battery term post. Now, this little gray or brownish area here is kind of an insulator, and right here is a fuse. It's called an MR Marine Battery Fuse, and they're available anywhere from 5 to 300 amps in about every increment you can think of. Then you would take your radio power wire, you connect it right here, put the cap on, you're good to go. You can't get any closer to battery, and the reason for that, the fuses protect wires. They don't protect your equipment. They protect the wire, and if you go downline from the battery, you leave that that section of wire unprotected without a fuse, so you always want to be right on the source. Okay? In your vehicles, from your radio, they will provide a raceway. They're along your door scut plates. Just pop them off with a screwdriver. They even make some special tools that you can pry that stuff off, but you don't need to buy that. I find a spatula from the kitchen actually works pretty good. Okay, don't roll up slack on your power cables or coax. Cut them to length. If you need to move them, you can buy new jumpers and coax. But, keep all your radio cables as far away from vehicle wiring as you possibly can. If you got to cross it or come in contact with it, do so at right angles. Your radio ground wire, this one here is important. You want to measure it in inches, not in feet. I've never seen a vehicle where you could not use a seat bolt and get a good connection. Or if you look under the seats, especially trucks and luxury vehicles, under the driver's seat and passenger seat, you'll find ground hard points. Look for the vehicle cable harnesses, and you'll see what they look like. They may be bolted to the floor. Those bolts undo that lug, and you'll see that cable is actually a metal tab. And what it is, it's a shield of the factory cable harness, and that's the ground that they're using to pick up hard ground points. So like you got power seats, heated seats, inverters, they go under seats for factory ads. So they've got some high current grounds that are there. Look for them and find them. Mount the radio as close to the antenna as possible, and never for any reason install a fuse on your radio negative lead unless you intend to connect it directly to the battery term post. And if you do that, label it dummy fuse. And that's all I got.
All right. Let's see. Let me switch this around here. Do you want to cancel your screen share?
Yep, I can do that.
All right. Good. So now I got you there. So I think we've got, let's see, we've got about 5 minutes or so. People have been very happy in the chat, and some of the information you've covered, just fantastic, of course. But, tell us a little bit more about this jumper in the power supply. I have an MFJ, I have an Amtron, I have a new MAR, and all of them did have this jumper. And I found the jumper on both the positive and the negative of the 12-volt DC posts. Okay, so right where you connect your battery, there is a little jumper wire to chassis ground on the positive and the negative. But a lot of times I'm seeing, is that a diode I see in there?
Jason, you've probably seen a capacitor. Now think about
Capacitor.
what you just said. If you took a wire from negative to chassis and positive to chassis, that's a direct short. That's not even possible.
So they're using a
that's the same as
diode.
connecting the wire. Okay, so more than likely what you're seeing is a capacitor, and capacitors are fine. That would be for a common mode noise.
Okay.
Okay, but I don't like them. I'm not going to tell anyone to take those out, but look for what you really want to find, and it's going to be in most. I'm not going to say all DC power supplies made for AMs, but the majority of them, and the big one that usually always has it is the Astron.
Okay.
Okay, it's a very visible jumper, but you don't. The thing about a transformer. There's two ways you can bond the secondary for protection. There's one called separately derived in NEC and non-separately derived. We use transformers to isolate the electrical systems from each other. So if we use the chassis to bond the secondary, like we do in the Astron, you've made a galvanic or DC bond across your transformer. You've lost your isolation. But if we take that same ground, if we want to ground the output, we come from the single point ground to either the positive terminal or the negative terminal. We don't have a loop in. We don't have to worry about that with our radio systems. Think about it. We've already got that bond made. It's been made for us.
Right. So
It's your radio.
So the bond jumper inside your power supply, is that going to be there on the AC side of it?
No. What you're going to see, what I've generally seen on most Astrons and any of them, it's going to be a physical wire jumper, either on, where the black terminal is on the back of an Astron.
Okay.
You'll actually see the newer one that's on the outside.
Okay.
You can actually physically take it. The older models, I forget what year it was. Hopefully someone might know and tell us. But it's done on the inside. It could either be done on the board, the voltage regulator board, or straight to the output terminal. But look for it. If you see it with the DC meter, just start looking for it. You'll find it. Start lifting wires. Once you find it, undo it. Check with the ohm meter again. Make sure it's open. You're good to go.
And how do you feel about those capacitors that I've discovered on the ones I have? The capacitors there on the DC posts to chassis ground.
I'm not a fan of them because I don't
What if they fail?
want to inject anything into the AC ground. Leave them. I'm going to tell you to leave them there. There's no reason doesn't do those. There's no good reason doesn't do them. Just because I don't like them is not a good reason doesn't do it.
Got it.
They are acting as filters, common line filters, but where that really gets to be a problem is on the AC. If you look on your Astrons, you will see some like the filters I talked about, the line filters. You'll see MOVs and capacitors installed from line to ground. Get rid of them.
Got it. Yeah.
If you see an Astron, you'll see them. Get rid of them. Not the one from line to now. The ones running from line to neutral are fine. Line to chassis are bad.
All right. Yeah, it looks like a picture is worth 1,000 words. Maybe I'll open up a power supply on a future video. Take a look. Obviously, unplug it. There was a question
I've
earlier.
got 3 here at the house. I can show you someday.
Okay, sure. Yeah, if you want to bring over some pictures sometime, email. So let's see. Someone asked, what is it meant by bringing coax in with the AC service? Ladder line, is this ladder line issues too? I guess this is going off of, how you recommend bringing coax into your house.
Okay. Well, the purpose of bringing it to your AC service is so we can bring those two grounds together.
Got it.
Okay? If you do that, you don't have to do all this special stuff. You just put a small little termination bar, there's your GEC, expand your ground electrode system, bond your coax there, then bring your 6 gauge and coax in. That doesn't mean you have to drill a hole in your house and come straight through the attic. You can bring it on the outside of the house if you need to. So you
Okay.
don't have to get it up in your attics and crawl spaces and try to figure out how to do that. That's exactly how your cable TV or telephone company is going to do it. But you need to bring, instead of routing that coax from your tower straight to the shack, go to the AC service first, bond it, and then bring it all inside.
Great.
Because if you're going to sink that rod outside your shack, you still got to dig that trench around and bond it to your AC service ground. Save yourself all that trouble. Bring it to the AC service to begin with. And then
Awesome.
expand your ground system
This
from
is a
your
real
AC service
B&H
going back
customer
out to the
story.
tower, not that back to the shack.
Well, Dereck, I can't thank you enough. This has been fantastic. Chances are there is going to be a load of questions in my comments. So I think we might have to have a chat in the future. But right now, right now we're going to slide on over to Adam, K6ARK. He is live. So I'm going to give it to Adam. Guys, 7-3, everyone, thanks for joining us. All right.